Every star you see will one day go dark. For centuries, the ultimate fate of our cosmos was a topic for philosophers and dreamers. But today, it is a field of hard science undergoing a revolution. New discoveries are completely reshaping our understanding of how the universe will actually end. By the end of this, you will know the leading theories, from a silent freeze to a violent rip, and the cutting-edge data pointing to which finale is most likely. We are piecing together the final episode of reality itself, a story written in the fading light of supernova and the whisper of gravitational waves. What feels more permanent than the universe around us? The most enduring prediction for our cosmic finale is a slow, silent fade. This is the Big Freeze, or the heat death of the universe, a theory rooted in one of physics' most fundamental laws, the second law of thermodynamics. It states that entropy, which is a measure of disorder, always increases in an isolated system. Think of a steaming cup of coffee left on a table. It doesn't stay hot forever. The heat energy spreads out, dissipating into the cooler air of the room until everything reaches the same lukewarm temperature. At that point, no more heat can flow and no useful work can be done. The universe on the grandest scale is that ultimate isolated system. Now, apply that principle across all of space and time. Every star is a temporary reservoir of concentrated energy burning brightly against the cosmic cold. But stars, like that cup of coffee, are constantly radiating their heat out into the vastness. Given enough time, trillions upon trillions of years, the last stars will exhaust their fuel and wink out. Black holes will slowly evaporate through a process called Hawking radiation. All the energy that once powered galaxies, forged planets, and sparked life will have become uniformly smeared across an ever-expanding void. This is the essence of heat death, a state of maximum entropy where everything is the same temperature, just a fraction above absolute zero. There are no hotspots left to drive engines, no energy gradients to power any process. It is the ultimate equilibrium, a static and eternal darkness where time itself loses all meaning because nothing ever changes. For over a century, this has been the textbook ending, supported by our observations of an accelerating expansion. The universe isn't just growing, it's stretching space itself, ensuring that this final, cold uniformity is inevitable. But is this quiet fade the whole story, or is the cosmos capable of a more dramatic final act? Yet the idea of a silent, eternal freeze feels almost too bleak to be the only answer. What if the story isn't linear but cyclical? This brings us to a once popular alternative, a cosmic rebound known as the Big Crunch. In this dramatic finale, the relentless pull of gravity finally overcomes the universe's expansion. Galaxies which have been flying apart for billions of years would begin to slow their retreat. Then they would stop, and then they would start rushing back together. Imagine the entire history of the cosmos playing in reverse. Distant galaxies would grow brighter and larger in our sky, their light blue-shifted as they accelerate toward us. The cosmic background radiation, the fading echo of the Big Bang, would heat up. Space itself would begin to contract, carrying all matter and energy on a collision course toward a single, unimaginably dense point, a singularity. It would be a catastrophic and fiery end, a mirror image of our explosive beginning. For a long time, this model held a powerful appeal. It offered a kind of cosmic poetry, a universe that breathes in and out in an endless cycle of birth, death, and rebirth. The gravitational muscle for this reversal was thought to come from all the matter in the cosmos, especially the mysterious dark matter whose unseen pull helps hold galaxies together. If there was enough of it, its collective gravity could one day put the brakes on everything. However, the discovery of dark energy in the late 1990s changed the game entirely. Observations of distant supernova revealed that the expansion of the universe isn't slowing down, it's speeding up, some repulsive force woven into the fabric of space itself, is pushing galaxies apart ever faster. This finding essentially pulled the emergency brake on the Big Crunch theory. With dark energy in the driver's seat, a gravitational reversal seems highly unlikely. So while the poetic symmetry of a cyclical universe remains a captivating thought experiment, the current evidence points firmly away from a grand collapse. But if dark energy is calling the shots, steering us away from a crunch and toward a freeze, could its influence lead to an ending even more strange and violent than either? But dark energy presents a far stranger possibility than a mere cold fade. What if the force accelerating the expansion isn't constant but grows stronger? This leads to the most violent finale imaginable, the Big Rip. In this scenario, dark energy transforms into something theorists call phantom energy, a substance with truly bizarre properties. Its repulsive power wouldn't just push galaxies apart, it would increase relentlessly, becoming infinite over time. To understand the horror of this, you need to grasp what holds reality together. Right now, the expansion of space is noticeable only on the vast distances between galaxy clusters. Within a galaxy like our Milky Way, gravity is the dominant force binding stars together. Within our solar system, the Sun's gravity holds the planets in their orbits. On Earth, gravity keeps you grounded, and the electromagnetic force holds the atoms in your body together. These forces create a hierarchy of structure from the cosmic web down to the particles that make up everything you see and touch. Phantom energy would dismantle this hierarchy from the largest scale to the smallest. It would start by shredding the cosmic fabric itself. Billions of years from now, as phantom energy's strength grows, the expansion would become so ferocious that it would overcome the gravitational glue holding galaxy clusters together. They would be violently flung into the isolating darkness. Next, the force would turn inward. The gravitational bonds holding individual galaxies together would snap. Stars would be torn from their galactic homes, sent careening into an ever-accelerating void. Then it would reach our solar system. The Sun's gravitational grip on Earth would be broken. Our planet would be ripped from its orbit, a lonely wanderer in an exponentially stretching emptiness. But the destruction wouldn't stop there. As the phantom energy density soars, it would eventually overcome the forces holding planets and stars together. Earth itself would be torn apart, mountains and oceans shredded as the very rock and metal succumb to the stretching of space. In the final moments, mere instants before the end, the expansion would reach down to the atomic scale. The electromagnetic force that binds electrons to nuclei would fail. Every single atom in what was once a universe would be violently disassembled. In the end, not even atomic nuclei would survive. The fundamental fabric of space-time itself would be stretched to a singularity, a point of infinite distortion where physics as we know it ceases to exist. It would be a finale of absolute disintegration, leaving behind not even cold, dormant particles, but a formless, chaotic void where not even the concept of structure remains. The Big Rip is a timeline of total annihilation, a systematic unraveling of every layer of reality. While the Big Freeze offers a quiet, eternal stillness, and the Big Crunch a fiery rebirth, the Rip is pure, unadulterated erasure. So which of these fates does our universe face? The answer lies in a single critical number that astronomers are desperately trying to measure. This critical number is known as the equation of state parameter, essentially a measure of dark energy's pushiness. But there is another, even more exotic possibility that doesn't rely on dark energy at all. It suggests our universe's end could come not from a grand cosmic force, but from a random quantum fluctuation. This is the theory of vacuum decay, and it proposes that our entire reality is built on a foundation that is fundamentally unstable. To understand this, you have to think of the universe not as empty space, but as a field of energy, a kind of invisible substrate that permeates everything. According to our best theories, this field might not be in its lowest possible energy state. Instead, our cosmos could be sitting in what physicists call a false vacuum. Imagine a ball resting in a small dip on the side of a steep hill. It seems stable for now, but it's not at the bottom of the hill. That lower point represents the true vacuum, a state of absolute minimum energy. Our universe is that ball perched in its little valley. It's been there for nearly 14 billion years, so it feels perfectly solid and permanent. But quantum physics tells us that nothing is ever perfectly still. Particles can tunnel through barriers, appearing on the other side as if by magic. In the same way, a tiny, random quantum event somewhere in the cosmos could nudge the universe out of its false vacuum valley. If that happens, a bubble of true vacuum would form. The laws of physics inside this bubble would be completely different from our own. Fundamental constants like the speed of light or the strength of gravity could be altered, making the chemistry of life, even the existence of atoms as we know them, impossible. This bubble would then expand in all directions at the speed of light. There would be no warning. One moment the universe is normal, the next an invisible wall of new physics is upon you. From your perspective, you would simply cease to exist along with every star, galaxy, and physical law you've ever known. It would be less of an explosion and more of a cosmic reset button, instantly overwriting reality with a new set of rules we cannot comprehend. The chilling part is that because it would expand at light speed, you could never see it coming. The end would be both instantaneous and absolute. While this sounds like science fiction, it is a legitimate, though highly speculative, consequence of our current understanding of quantum field theory and the Higgs boson. It reminds us that the stability of reality itself might be an assumption, not a guarantee. So with endings ranging from a silent freeze to a quantum reset, how do we determine which path our universe is actually on? The answer lies in the faint, ancient light from the very beginning. The ultimate fate of the universe hinges on a mystery we cannot see. This is the puzzle of dark energy, the invisible engine that is not just expanding our cosmos, but accelerating its flight into the future. Its story begins not with a telescope's first light, but with a profound shock in the late 1990s. Two independent teams of astronomers were meticulously studying a specific kind of stellar explosion, a Type 1, a supernova. These cosmic bombs are crucial because they always explode with nearly the same intrinsic brightness, making them perfect standard candles. By measuring how bright they appear from Earth, scientists can calculate their distance with incredible precision. Simultaneously, by analyzing the redshift of their light, how stretched it has become by the expanding universe, they can determine how fast the galaxy hosting that supernova is moving away. The expectation was that the gravity of all the matter in the universe would be acting like a brake, gradually slowing the expansion that started with the Big Bang. The data delivered a stunning reversal. The most distant, ancient supernova were dimmer than they should have been. This meant they were farther away than predicted, which in turn meant the universe was not slowing down at all. In fact, it was speeding up. Some repulsive force was overpowering gravity on the largest scales, pushing galaxies apart faster and faster. This discovery was so monumental, it earned the lead researchers the Nobel Prize in Physics in 2011. So what is this force? The leading explanation is that dark energy is a property of space itself. Think of empty space not as true nothingness, but as a seething quantum foam, constantly bubbling with virtual particles that flicker in and out of existence. This activity gives the vacuum of space an inherent energy density. According to Einstein's equations, this vacuum energy exerts a negative pressure, which acts as a kind of anti-gravity, causing space to stretch. If this energy density remains constant as the universe expands, it is called the cosmological constant. This scenario points us firmly toward the long, cold fade of the Big Freeze. But here is the critical uncertainty that determines our destiny. What if dark energy is not constant? What if it is a dynamic field, something theorists call quintessence that can change over time? Its strength could weaken, which might allow for other, more exotic endings. Or, terrifyingly, it could strengthen, evolving into the phantom energy that would trigger the Big Rip. The simple truth is this: the precise nature and behavior of dark energy is the single most important factor in the cosmic endgame. It is the dial being turned that chooses between a silent eternity, a violent disintegration, or something else entirely. To read that dial, we must look back to the very beginning. The key to this mystery lies in a single, deceptively simple number, the Hubble constant. It is the universe's current expansion rate, a measure of how fast galaxies are receding from us for every megaparsec of distance. Think of it as the cosmic speedometer, telling us how quickly the fabric of space is stretching right now. For decades, astronomers have worked to pin down this number with ever greater precision. Yet instead of converging on a single answer, the most sophisticated experiments in the world are telling two different stories, creating a rift in cosmology known as the Hubble tension. On one side, we have the view from the beginning. By studying the detailed patterns in the cosmic microwave background, the afterglow of the Big Bang, the Planck satellite provided an exquisitely precise measurement. It tells us what the Hubble constant should be, based on the infant universe's conditions and our standard model of cosmology. On the other side, we have the view from our cosmic neighborhood. Teams using the Hubble Space Telescope and other observatories look at pulsating stars called Cepheid variables and brilliant supernovae in nearby galaxies. These are our cosmic yardsticks, allowing us to measure distances and recession speeds directly. The problem is this: the local measurements consistently give a faster expansion rate than the prediction from the early universe. The numbers disagree by a small but significant amount, a difference that has stubbornly persisted despite years of rechecking and improved data. This isn't just a minor accounting error. It is a fundamental tension. It suggests that something in our understanding is incomplete or wrong. Perhaps dark energy is not constant but changing in strength. Maybe there is an unknown type of neutrino or another exotic particle from the early universe subtly altering the cosmic expansion history. Or, most intriguingly, it could point to a flaw in our standard model of cosmology, the lambda CDM model, which has been the backbone of our understanding for a generation. This tension matters profoundly for the ultimate fate. If the local, faster measurement is correct, it implies the universe is expanding more briskly than we thought. That could tilt the scales, making a Big Rip scenario more plausible if that acceleration is driven by a strengthening form of dark energy. Alternatively, if the early universe measurement is the true guide, our current models might need a tweak, but the long-term forecast of a big freeze remains intact. The Hubble tension is not a failure of science, it is a beacon. It illuminates the edge of our knowledge, hinting that the cosmos still holds profound secrets about its own engine, and therefore its final destination. That cosmic speedometer reading is only half the story. To truly predict the end, we must also understand the shape of the universe itself. This isn't about stars and galaxies, but the underlying geometry of space on the grandest possible scale. Is our cosmos flat like an endless sheet of paper, open like a saddle that curves away forever, or closed like the surface of a giant sphere? This geometry is not an abstract concept. It is a direct reflection of the universe's total density, the combined weight of all matter, energy, and dark energy. And that density is the ultimate arbiter of fate. For decades, the leading answer from our most powerful observatories, like the Planck satellite, has been remarkably clear. The universe appears to be geometrically flat. This finding is monumental. A flat geometry means the universe's density is at a precise, critical value, perfectly balanced between the forces of expansion and gravity. In such a universe, parallel laser beams shot across the cosmos would never meet or diverge. They would travel on forever, side by side. This flatness aligns perfectly with the story of eternal expansion driven by dark energy. pointing us inexorably toward the long, cold fate of the Big Freeze. But science thrives on precision, and here lies a fascinating caveat. Our measurements, while incredibly accurate, still come with a tiny margin of error. The data says the universe is flat to within a razor-thin tolerance of about 0.2%. That might sound insignificant, but on the scale of the entire cosmos, it leaves the door open for a universe that is ever so slightly curved. If that curvature is positive, if the universe is a closed sphere, then its expansion could one day halt and reverse, leading to a big crunch. If the curvature is negative, an open saddle shape, the expansion could accelerate even more violently than we predict. The quest to measure this fundamental property is far from over. Next-generation telescopes and space missions are being designed with one goal: to probe the cosmic microwave background and the large-scale structure of the universe with unprecedented sensitivity. They are hunting for the faintest imprints of primordial gravitational waves or subtle distortions in the light from ancient galaxies that could reveal a curvature too slight for Planck to see. So while the evidence strongly favors a flat universe and a frozen end, we must remain humble. The final chapter of reality could still hinge on a decimal point we haven't yet seen. This single number, W, is the master dial for our cosmic fate. In the equations of cosmology, it is called the equation of state parameter, and it describes the pressure that dark energy exerts. Think of it as a personality profile for the most mysterious force in the universe. If W is exactly -1, dark energy behaves as Einstein's cosmological constant, a steady, unchanging presence woven into space itself. This is the scenario that leads to the long, gradual expansion of the Big Freeze, where the universe cools into eternal silence. But if W is less than -1, the personality changes dramatically. This is phantom energy, a substance whose repulsive power grows stronger as the universe expands. That increasing push is what would eventually overcome every binding force, leading to the catastrophic disintegration of the Big Rip. The difference between a frozen eternity and a shredded reality hinges on whether this number is exactly -1 or just a fraction below it. For years, every measurement has suggested W is incredibly close to -1, consistent with a cosmological constant. But close is not the same as exact. The ghost of a possibility remains that dark energy is not constant at all, but a dynamic field slowly changing over billions of years. This is where our newest generation of cosmic detectives comes in. Projects like the Dark Energy Survey have spent years mapping the positions and shapes of hundreds of millions of galaxies, looking for subtle clues in how the large-scale structure of the universe has evolved. They are measuring W by observing how the acceleration of the universe has changed over cosmic history, using the distribution of galaxies as a fossil record of expansion. Their latest results continue to pin W very near -1, but the error bars, while shrinking, still leave a sliver of room for phantom energy. The pursuit is about to enter a new era. The Vera C. Rubin Observatory, with its enormous mirror and gigantic camera, will soon begin the legacy survey of space and time. It will not just map galaxies, it will create a motion picture of the sky, cataloging billions of objects and detecting billions more fleeting events. This unprecedented torrent of data will measure the cosmic acceleration with a precision we can barely conceive of today. It will either finally confirm that W is exactly -1, locking in the forecast of a Big Freeze, or it will make the monumental discovery that it is not. A definitive measurement that W is less than -1 would be a scientific earthquake, forcing us to rewrite the final chapter of everything. It would mean the universe is not headed for a quiet end, but for a violent and ultimate dissolution. We are, right now, on the cusp of knowing which timeline is ours. The most precise cosmic ruler wasn't built in a lab, but forged in the fires of the Big Bang itself. This ruler is etched into the very structure of the universe, a fossilized echo of its earliest moments known as Baryon acoustic oscillations. To understand them, you must travel back to a time before the first stars, when the cosmos was a seething, opaque plasma, a thick soup of particles and light. In that primordial fluid, gravity tried to pull matter together into clumps, but the intense pressure of radiation pushed back, creating powerful sound waves that rippled outward. These were not gentle waves, but titanic pressure fronts racing through the infant universe at over half the speed of light. Then, about 380,000 years after the Big Bang, everything changed. The universe expanded and cooled enough for atoms to form, allowing light to travel freely for the first time. In that instant of transparency, the sound waves froze in place, their final crests and troughs imprinted as subtle over-densities in the distribution of matter. Think of it like dropping a pebble into a pond and then instantly freezing the water solid. The ripples are preserved, a perfect snapshot of the wave at the moment it stopped. In the cosmic pond, that frozen ripple left a specific signature, a subtle preference for galaxies to be separated by a certain scale, about 500 million light-years apart. This scale becomes our standard ruler. Because we know its original size from the physics of the early universe, we can measure how much it appears stretched or compressed in the sky at different distances, and thus at different eras of cosmic history. By surveying millions of galaxies and measuring their separations, astronomers can see this faint statistical imprint. It tells them exactly how much the universe has expanded between the time the light left those ancient galaxies and today, providing a direct three-dimensional map of the expansion history. This is where a new generation of instruments is changing the game. The Dark Energy Spectroscopic Instrument, known as DESI, is a monumental project mounted on a telescope in Arizona. It doesn't just take pictures of galaxies, it uses 5,000 tiny robotic fibers to capture the light from 5,000 individual galaxies at a time, precisely measuring their redshifts to map their positions in three-dimensional space. Its goal is to create an unprecedented map of the cosmic web, charting the positions of tens of millions of galaxies and quasars. With this immense catalog, scientists can trace the Baryon acoustic oscillation signal with breathtaking precision across vast stretches of cosmic time. Why is this so crucial for our ultimate fate? Because it gives us an independent and incredibly robust measurement of how dark energy has behaved over billions of years. Supernova measurements are brilliant but rare standard candles. The cosmic microwave background gives us a single snapshot of the infant universe. Baryon acoustic oscillations provide a continuous ruler, a measuring tape stretched across the cosmos that lets us check the expansion rate at many different epochs. Early results from DESI and other surveys are already confirming the accelerated expansion, and they continue to constrain that critical number, the dark energy equation of state, with ever-tightening precision. They are another line of evidence narrowing down the possibilities, helping to rule out certain models of phantom energy or quintessence. Every new galaxy mapped is another data point in the cosmic ledger, bringing us closer to answering whether the force driving our universe apart is a constant whisper or a growing shout. But perhaps the most direct way to measure the universe's expansion is to listen to its most violent events. This is the promise of gravitational wave cosmology, a field born from one of science's greatest triumphs. In 2015, the LIGO Observatory made the first ever direct detection of gravitational waves, ripples in the fabric of spacetime itself, caused by the collision of two black holes over 1 billion light-years away. That discovery didn't just confirm a century-old prediction by Einstein, it opened an entirely new window on the cosmos, one based not on light but on the shudder of gravity. These waves carry with them a unique and powerful piece of information. When two incredibly dense objects like black holes or neutron stars spiral together and merge, the gravitational waves they emit have a very specific signature. The frequency and amplitude of the waves, the cosmic chirp, directly tell us the masses of the objects involved. This is crucial. By knowing the intrinsic strength of the event from the waveform and measuring how faint or strong the signal is when it reaches Earth, astronomers can calculate the distance to the merger with remarkable precision. This makes these cataclysms standard sirens, a new class of cosmic distance markers that operate on pure gravity, completely independent of the cosmic ladder built on starlight. The power of this method was demonstrated spectacularly in 2017, when LIGO and its European counterpart, Virgo, detected gravitational waves from a pair of colliding neutron stars. For the first time, telescopes around the world and in space saw the brilliant flash of light from the same event, a kilonova. By combining the gravitational wave distance with the traditional redshift measurement from the accompanying light, scientists could make a direct, clean measurement of the Hubble constant. This single event provided a value that intriguingly landed right in the middle of the ongoing tension between early and late universe measurements. It was a proof of concept that standard sirens could be the ultimate arbiter. The future of this field is even more breathtaking. While ground-based detectors like LIGO listen for the high-frequency chirps of stellar mass black holes, a space-based observatory named LISA is on the horizon. Scheduled for the 2035, LISA will consist of 3 spacecraft flying in a giant triangle, millions of kilometers apart. It will detect gravitational waves at much lower frequencies, allowing it to hear the mergers of supermassive black holes from the dawn of time. These colossal events, occurring when the universe was just a fraction of its current age, will provide standard sirens from deep cosmic history. By comparing their distances and redshifts, we will trace the expansion of the universe across billions of years with a clarity we've never had. This could finally resolve the Hubble tension, telling us definitively which expansion rate is correct. More profoundly, it will give us an entirely new, gravity-only dataset to probe the behavior of dark energy. Does it have always been constant, or does its influence change over time? The silent tremors from these ancient collisions may carry the answer in their waveforms, offering insights into the cosmic endgame that light alone could never reveal. Yet even the most violent or silent end for our universe might not be the final word. There exists a theory so vast it redefines the very meaning of beginning and end. This is the concept of eternal inflation and the multiverse, a vision where our entire cosmos is just one bubble in an endless, frothing sea of reality. It all stems from a refinement of the Big Bang theory known as cosmic inflation. In the first fleeting fraction of a second, scientists believe the universe underwent a period of hyper-expansion, inflating from a subatomic speck to something macroscopic in an instant. This explains the remarkable uniformity and flatness we observe today. But what if that inflationary process never completely stopped? The theory of eternal inflation proposes that the energy field driving that initial burst, the inflaton field, decayed in most places to form stable universes like our own. But in other regions, it remained potent, continuing to inflate at an exponential rate. In this picture, our universe is a single bubble of stable space that nucleated within an eternally inflating background. And we are not alone. New bubbles are constantly forming in that hyper-expanding sea, each one a separate universe with its own random set of physical laws and constants. Some might have stronger gravity, making stars burn out in an instant. Others might have no dark energy at all, collapsing back in a big crunch shortly after birth. In an eternally inflating multiverse, beginnings and endings are local events. Our Big Bang was simply the moment our particular bubble of stable space formed. And our ultimate fate, whether a big freeze or a big rip, is just the story of this one bubble. While our local cosmos may grow dark and cold or be torn apart, the greater multiverse continues its relentless, timeless expansion, giving birth to an infinite number of new universes forever. This shifts the philosophical ground entirely. The end of everything we know becomes not a universal finale, but a regional occurrence. It suggests that existence itself, in the grandest sense, may have no end and no beginning, only an endless cascade of cosmic possibilities. While this idea is currently beyond the reach of direct experimental proof, it emerges naturally from the mathematics of inflation. It forces us to confront a humbling scale. Our entire history, from the first star to the last black hole, might be just a single chapter in a book with infinite pages. Even the last titans will not endure forever. In the deep, dark future of a universe headed for a big freeze, after the final stars have burned out and the galaxies have drifted into darkness, only one class of object will still command the void: black holes. These cosmic monsters, born from the collapse of massive stars and the mergers of galaxies, will become the final significant structures in a dying cosmos, the last landmarks in an endless sea of expanding night. Their reign, however, is not eternal. They too are subject to a slow, inexorable decay, a process predicted by Stephen Hawking that ties the immense gravity of general relativity to the fuzzy uncertainty of quantum mechanics. This is Hawking radiation, and it dictates the ultimate fate of the last celestial objects. To understand how a black hole, the very definition of a gravitational prison from which not even light can escape, can possibly evaporate, you have to peer into the quantum foam that fizzes at the edge of reality. According to quantum theory, empty space is not empty. It is a seething sea of virtual particles, pairs of matter and antimatter that spontaneously pop into existence, borrow energy from the vacuum, and then almost instantly annihilate each other, returning the energy. This happens everywhere, all the time. Now, imagine this process occurring right at the event horizon of a black hole, the point of no return. In a rare but statistically inevitable event, one of these virtual particle pairs can be born such that one particle falls across the horizon while the other escapes into space. The particle that falls in has negative energy, which effectively reduces the mass of the black hole by a tiny, almost imperceptible amount. The particle that escapes becomes real, carrying away a minuscule bit of the black hole's energy. This is Hawking radiation. From a distance, it looks as if the black hole is glowing with a faint, theoretical heat, slowly bleeding mass into the universe. The timescales involved are beyond human comprehension, numbers so vast they lose all meaning. For a stellar mass black hole, the kind left behind by a large star, the evaporation process would take about 10 to the 67 years. That's a 1 followed by 67 zeros. For the supermassive black holes that anchor galaxies like our Milky Way, with masses millions or billions of times that of our Sun, the timeline stretches to an almost ludicrous 10 to the 100 years. To grasp that scale, consider that the entire current age of our universe is only about 10 to the 10 years. These black holes will outlast everything else by epochs upon epochs. Picture this far future era. The universe is profoundly dark and cold, expanded to such a degree that the nearest black hole is an inconceivable distance away. No stars illuminate the sky. The cosmic background radiation has cooled to a whisper barely above absolute zero. The only notable events in this near eternity are the occasional, incredibly rare pop of a particle as a black hole somewhere in the void emits another quantum of Hawking radiation. As a black hole evaporates, a strange thing happens. It heats up. The smaller a black hole gets, the faster it loses mass and the hotter its Hawking radiation becomes. The final moments are not a slow fade, but a sudden, violent release. When the black hole's mass becomes extremely small, the evaporation accelerates in a runaway process. In a final burst of energy, it would vanish in a flash of particles and gamma rays, a brief, brilliant spark in the endless dark that leaves behind only a diffuse cloud of fundamental particles. And then there is nothing, no structures, no clumps of matter, no hot spots or cold spots. every black hole, the last organized repository of mass energy in the cosmos, will have dissolved into a uniform, ultra-thin haze of photons, neutrinos, and other elementary particles, spread perfectly evenly across an astronomically vast and ever-expanding space. This moment, the evaporation of the last black hole, marks the true beginning of the heat death's final act. It is the point where the universe achieves maximum entropy, a state of perfect equilibrium where nothing can ever happen again. Time, in any meaningful sense, ceases to have a purpose, but could this profound silence, this absolute end of change, ever be broken? But the silent fade of heat death might not be the final word on matter itself. Deep within every atom that makes up the stars, the planets, and even our own bodies, there could be a hidden timer counting down to an end more absolute than any freeze. This is the speculative, haunting possibility of proton decay. We are taught that protons are stable, permanent fixtures of the universe. Along with neutrons and electrons, they are the fundamental building blocks of all the tangible things we see and touch. But some of our most ambitious theories of physics, known as grand unified theories, suggest this permanence is an illusion. These theories attempt to merge the electromagnetic, weak, and strong nuclear forces into a single, elegant framework. And within that framework, a startling prediction emerges. The proton, the very heart of the atomic nucleus, may not be immortal. It could, over unimaginable eons, spontaneously decay. Imagine the bedrock of reality itself slowly turning to dust. If protons are unstable, then every atomic nucleus in existence is ultimately doomed. A proton would not explode or shatter in a conventional sense. Instead, through a rare quantum process, it could spontaneously transform into lighter particles, like a positron and pions, which would then quickly decay into pure radiation gamma rays and neutrinos. The matter you are made of would not just grow cold, it would literally unravel, dissolving into a faint whisper of energy. The timescale for this process, if it exists at all, is almost incomprehensibly vast. Experiments deep underground, designed to detect this elusive decay, have so far seen nothing. This tells us that if protons do decay, their average lifetime must be staggeringly long, likely greater than 10 to the 34 years. To put that number in perspective, the current age of the universe is only about 10 to the 10 years. We are talking about a duration a trillion times longer than the cosmos has even existed. In the timeline of a heat-death universe, this means that long after the last stars have died and the last black holes have evaporated, the frozen, dormant remnants of planets and stars would still be sitting in the dark. They would be cold, dead husks, but they would still be made of atoms. But if proton decay is real, even these ghostly relics would not last. Over these monstrous eons, the very protons in their cores would, one by one, flicker out of existence. A frozen Earth, a white dwarf star, the scattered debris of ancient galaxies, all of it would gradually and silently disintegrate into a diffuse fog of leptons and photons. It is the ultimate erasure of structure, leaving behind a universe where not even atomic nuclei remain intact. This prospect adds a chilling, deeper layer of desolation to the heat-death scenario. It is not enough for the universe to grow cold and dark. Every last monument to its once vibrant history would be systematically annihilated, leaving no record that anything had ever been here at all. The search for proton decay is, in essence, a search for the universe's ultimate expiration date. Its discovery would rewrite our understanding of matter and force us to confront a cosmos where nothing, not even the building blocks themselves, is built to last. The idea that nothing lasts forever might be the ultimate rule, but some theories dare to challenge it with a vision of cosmic immortality. This is the return of the cyclical universe, reimagined through the lens of modern physics with concepts so elegant they border on the poetic. One of the most compelling is called conformal cyclic cosmology, proposed by the renowned physicist Roger Penrose. It suggests that the distant future of our universe and the fiery birth of the next are, in a profound mathematical sense, the same point. Here is how it works. In a cosmos dominated by dark energy and headed for a big freeze, all matter will eventually decay into massless particles like photons, and all black holes will evaporate via Hawking radiation. In this state, the universe becomes incredibly vast, cold, and empty, but also incredibly simple. There are no scales, no rulers, no clocks, because there are no massive particles to define distance or time. Penrose argues that this late-stage, featureless universe can be mathematically conformally rescaled, meaning its infinite expanse can be mapped onto the hot, dense, and equally featureless singularity of a new Big Bang. In this model, the end is not a true ending, but a transformation. The infinite future of one cycle becomes the zero-point beginning of the next. Even more astonishing, Penrose proposes that some information might bridge this transition. He suggests that the gravitational waves from supermassive black hole mergers in our universe could leave faint, circular imprints in the cosmic microwave background of the next cycle, like cosmic fingerprints passed from one creation to another. Teams are actively searching for these patterns, known as Hawking points, in the data from the Planck satellite. Another radical idea emerges from string theory, the quest for a theory of everything. This is the ekpyrotic or cyclic model involving colliding brains. Imagine our entire three-dimensional universe as a single membrane or brain floating in a higher dimensional space. Parallel to it floats another brain. These two worlds could periodically attract each other, collide, and then bounce apart. From our perspective inside our brain, that collision would release an immense amount of energy, appearing as a hot, dense, expanding universe, a Big Bang. After the collision, the brains separate. The universe within each one expands and cools, forming stars and galaxies, and then dark energy drives them apart. But gravity slowly draws them back together over trillions of years, setting the stage for another collision and another rebirth. In this scenario, a big crunch is replaced by a big bounce, a cosmic reset triggered by a collision in a hidden dimension. These theories offer a breathtaking alternative to a singular, final fate. They propose that the cosmos is not a one-act play but an endless epic, where each grand finale is merely an intermission. The search for evidence is what turns philosophy into science. For conformal cyclic cosmology, it is the hunt for those anomalous rings in the cosmic microwave background. For brain collisions, scientists look for specific signatures in the polarization of that same ancient light, or for subtle statistical anomalies in the distribution of galaxies that might hint at a pre-Big Bang structure. While still speculative, these ideas remind us that the ultimate end may be nothing more than a turn in an infinite cycle, a breath in the life of a universe that has learned how to begin again. The profound silence of a heat-dead universe might not be the final state. Quantum mechanics introduces a wild card into this eternal equilibrium, a rule that says true nothingness is impossible. Even in a perfect vacuum at the absolute zero of temperature, space itself remains restless. This is the realm of quantum fluctuations, where particles and energy spontaneously blink into existence, borrowing from the universe's ledger before vanishing again. In our current vibrant cosmos, these fleeting events are overshadowed by the grand drama of stars and galaxies. But in the far, far future, when the universe is cold, dark, and stretched into a featureless thin haze, these quantum jitters become the only game in town. Over timescales that make the age of black holes seem brief, something astonishing becomes not just possible but statistically inevitable, given enough time. And we are talking about time so vast the number has little meaning. A random quantum fluctuation could spontaneously assemble a hydrogen atom from the void. Given even more time, it could assemble a rock, a star, or even a planet. This leads to one of the most mind-bending thought experiments in all of physics, the Boltzmann brain. Named for the 19th century physicist Ludwig Boltzmann, It is a paradox born from probability in an eternal, nearly empty universe. The idea is this. In a state of maximum entropy and equilibrium, the most likely event is that nothing happens, but extremely unlikely events are not impossible. They are just incredibly rare. Given an infinite or near infinite amount of time, every possible configuration of particles, no matter how improbable, will eventually occur by random chance. It is statistically more probable for a fully formed, self-aware brain complete with false memories of a past life in a vibrant universe to spontaneously assemble from the quantum foam than it is for our entire complex, ordered cosmos to have arisen from a simple hot state. Think about that for a moment. In a universe that exists for all practical eternity, you are more likely to be a disembodied, momentary consciousness hallucinating a reality that never existed than you are to be a real person in a real universe with a real history. This isn't science fiction. It's a serious logical problem that cosmologists grapple with. It suggests that if our standard model of a heat death is correct, then you and I, and everything we experience, are far more likely to be random quantum accidents than the products of a 13.8 billion-year evolution. Most physicists consider this a reductio ad absurdum, a sign that our understanding of the far future is incomplete. It pushes us toward theories like a cyclical universe or a multiverse, where the overall context prevents such bizarre statistical freaks from being the norm. Yet the Boltzmann brain forces us to confront the truly alien nature of deep time and the probabilistic heart of reality. It implies that in a quiet enough cosmos, waiting long enough, even the impossible becomes merely a matter of patience. The universe might find a way to dream long after it has forgotten how to shine. But what if the universe is not a physical object at all? This brings us to a startling modern proposition that reframes the entire question of our end, the simulation hypothesis. If our reality is not fundamental but a sophisticated digital construct, then the ultimate fate of everything might not be a slow freeze or a violent rip. It could be as abrupt and simple as someone, somewhere, flipping a switch and shutting down the computer. This idea, once confined to science fiction and philosophy, has gained a surprising amount of traction in scientific and technological circles in recent years. The core argument is often attributed to the philosopher Nick Bostrom, who laid out a compelling trilemma. He suggested that at least one of three propositions is very likely true. First, that almost all civilizations go extinct before reaching a post-human stage capable of running simulations. Second, that advanced civilizations have no interest in running ancestor simulations of their past. Or third, that we are almost certainly living in a simulation. If a civilization survives and develops the technology to create vast, detailed simulations of conscious beings, and if they choose to run them, then the number of simulated minds would vastly outnumber the biological ones. Statistically, we would be more likely to be one of those simulations. From a purely probabilistic standpoint, it is a difficult argument to dismiss outright. Some technologists and physicists have even proposed ways to test the idea, looking for potential glitches or shortcuts in the fabric of reality, like tiny pixelations in the cosmic background radiation or anomalies in the behavior of high-energy particles. While no evidence has been found, the search itself highlights how the line between metaphysics and physics can blur. The implications for our cosmic finale are profound. An end by simulation shutdown bypasses all the complex physics of dark energy and proton decay. There is no heat death, no big rip, just an instantaneous termination of processing. One moment, reality exists in all its complexity and beauty. The next, there is nothing, not even empty space, because the very framework that defines space and time ceases to run. It is a digital apocalypse, silent and complete. Critics, of course, are quick to point out the flaws. The computational power required to simulate every particle in a universe let alone the conscious experience of billions of beings, is mind-boggling, perhaps physically impossible even for an advanced civilization. Others argue the hypothesis is untestable in any meaningful way, making it more of a modern philosophical puzzle than a scientific theory. Yet its cultural resonance is undeniable. It taps into a deep-seated intuition that our reality might be more fragile, more contingent than it appears. It asks us to consider whether the laws of physics are the bedrock of existence or merely the rules of the game, lines of code that can be overwritten or deleted at any moment. This makes for a captivating, if unsettling, thought experiment. It places our search for a cosmic endgame in a startling new context. We could spend eons measuring the equation of state of dark energy, only to discover the true controller of our fate is not a force of nature, but a decision made in a realm entirely beyond our perception. The most profound question may not be how the universe ends, but whether anything will be there to witness it. For all our talk of heat, death, and phantom energy, we have assumed a passive cosmos, a stage where life is merely a fleeting audience member. But what if intelligence, given enough time, could step onto that stage and influence the final act? This is a realm of pure speculation, yet it forces us to consider whether life itself could become a cosmic-scale force, shaping the destiny of everything. Imagine a civilization that survives not for millennia, but for billions of years, evolving into something we might call post-humanity. Its energy needs would be astronomical, its perspective measured in galactic rotations. Faced with the inevitable dimming of stars, such a civilization would not go gently into that cold night. Its first project might be stellar engineering on a staggering scale, building Dyson spheres or similar megastructures to capture the total energy output of stars, postponing the era of darkness. But stars are finite. The next almost inevitable step would be to turn to the last great power plants in a fading cosmos, black holes. Through theoretical constructs like the Penrose process or by feeding them carefully controlled streams of matter, a super-civilization could extract immense rotational energy from these gravitational beasts, potentially powering their existence for epochs longer than the entire current age of the universe. They might even learn to harvest the faint Hawking radiation itself, squeezing the last usable energy from the void. Yet this is still just delaying the inevitable within one dying universe. A truly ambitious civilization might set its sights on a more radical goal, triggering a new beginning. If our universe began with a phase of inflationary expansion, could a sufficiently advanced intelligence with a godlike command of energy recreate those conditions? The idea of artificially inducing a new inflationary bubble, a baby universe within the old one, is a staple of speculative cosmology. It might involve concentrating energy densities so extreme that they locally warp space-time into a new Big Bang, creating a separate cosmic domain with its own future. For the parent civilization, this could be an act of ultimate legacy, a way to seed a new reality even as their own winds down. An even more staggering prospect is migration. If theories of a multiverse are correct and other universes with different physical constants exist, perhaps a civilization could find a way to tunnel through the higher dimensional bulk, escaping their dying cosmos for a younger, more hospitable one. This would be the ultimate form of cosmic voyaging, not between stars, but between entire realities. While these ideas sound like the plot of the most ambitious science fiction, they are grounded in a logical extension of physics and survival. They transform the narrative from one of bleak, inevitable decline into a story of potential agency. They ask whether the purpose of intelligence in the very long run is to become a guardian of order against entropy, a tender of cosmic flames in an ever-darkening expanse. It offers a fragile but powerful hope that the final word on the universe's fate might not be written by mindless forces alone, but could one day be shaped by the very consciousness it accidentally spawned. Our sun has about 5 billion years of stable life left. That may seem like an eternity, but on a cosmic scale, it is a relatively near-term event. When its core hydrogen fuel is finally exhausted, our star will swell into a red giant, engulfing the inner planets, likely including Earth, before shedding its outer layers and leaving behind a cooling white dwarf cinder. This is the first major milestone on the long road to the end. Around the same time, or perhaps a little later, our galaxy is set for a spectacular collision. The Milky Way and its larger neighbor, the Andromeda Galaxy, are currently hurtling toward each other at over 250,000 miles per hour. In about 4 to 5 billion years, they will begin a slow gravitational dance, their immense spiral structures tearing each other apart over billions of years. Stars are so far apart that direct collisions will be rare, but the night sky from any surviving planets would become a breathtaking canvas of new stars and swirling gas before the two galaxies merge into a single, giant elliptical galaxy. This marks the end of our galaxy as we know it. Fast forward another 100 billion years or so. By this point, the accelerating expansion driven by dark energy will have carried all other galaxies beyond our cosmic horizon. The merged remnant of the Milky Way and Andromeda will be an island in an ever-darkening void with no other galaxies visible in the sky. The era of star formation will be long over, the last red dwarfs, the smallest, longest-lived stars having finally flickered out. This ushers in the degenerate era where the universe is lit only by the faint, residual glow of white dwarfs and neutron stars, slowly cooling over trillions of years. Next comes the black hole era. With all stars extinguished, black holes become the sole significant sources of gravity. They will slowly feed on the scant remaining dust and dead stars growing in mass. But even their reign is temporary. Through Hawking radiation, they too will evaporate. A stellar mass black hole might take 10 to the 67 years to vanish. The supermassive black holes at galactic centers will hold on for an almost incomprehensible 10 to the 100 years. Their final moments will be a brief, brilliant flash of gamma rays as they pop out of existence. After the last black hole evaporates, we enter the dark era, or the era of eternal darkness. The universe is now a cold, nearly perfect vacuum, filled only with an ultra-thin soup of photons, neutrinos, and other fundamental particles, all spread perfectly evenly by relentless expansion. If protons decay, even the frozen remnants of dead stars and planets will have disintegrated. This is the heat death, a state of maximum entropy where the temperature approaches absolute zero and no meaningful work can ever be done again. Time, for all practical purposes, loses its meaning. This timeline is not a prophecy of doom, but a map of inevitability written in the laws of physics. It stretches our imagination to its breaking point, forcing us to confront scales of time so vast they render human history a fleeting blink. Yet within this grand, cold narrative, a profound question remains. Does this inevitable fade to black represent a true end, or could it be a prelude to something entirely new? This grand timeline of cosmic endings might feel impossibly remote, a story with no bearing on our daily lives. Yet the quest to understand that final chapter is reshaping science here and now in our labs and observatories. Every measurement of a distant supernova, every map of the cosmic web, every attempt to detect a proton's decay is not merely fortune-telling for the universe. It is a direct assault on the greatest mysteries in physics. The search for dark energy, for instance, is forcing us to question the very nature of space and time. Is the vacuum truly empty, or is it a dynamic field with properties we barely comprehend? Understanding dark energy could be the key to unifying Einstein's theory of gravity with the quantum realm, a goal that has eluded physicists for a century. It is a puzzle that connects the fate of galaxies to the behavior of particles smaller than atoms. Similarly, investigating whether protons decay probes the validity of grand unified theories which seek to describe all fundamental forces as one. A single rare decay in a vat of water deep underground could rewrite the rulebook for how matter itself is built. This work is not abstract prophecy, it is the cutting edge of human knowledge. We are using the entire cosmos as our laboratory, and its ultimate destiny is the most extreme experiment we can observe. By studying how the universe will end, we are ultimately asking what it is made of and how it works at the most fundamental level. These questions strike at the heart of our existence. They force us to confront what reality truly is, whether time has an arrow, and if the constants of nature are truly constant or merely temporary settings in a much larger, stranger multiverse. The drive to solve these puzzles pushes our technology to its limits, from building gravitational wave detectors sensitive enough to measure a distortion smaller than an atomic nucleus, to creating satellites that map the faint afterglow of creation itself. In seeking the universe's end, we are not just looking outward into the distant future. We are looking inward, testing the limits of our own understanding and defining our unique place in the cosmic story. We are the universe becoming conscious of itself, and now we are trying to read its final thoughts. A universe that simply vanishes in a flash makes for dramatic fiction, but it bears little resemblance to our scientific forecast. One of the most persistent myths is the idea of an imminent or sudden cosmic collapse, the Big Crunch. While it remains a captivating concept of cyclical rebirth, the evidence we have today strongly argues against it. Remember the discovery of dark energy, that mysterious force accelerating the expansion. That finding didn't just add a new chapter to the story. It effectively closed the book on a gravitational reversal for our particular universe. The data from distant supernova and the cosmic microwave background shows the expansion is speeding up, not slowing down. For a big crunch to occur, gravity would need to win, pulling everything back together. With dark energy in control and pushing galaxies apart ever faster, that cosmic tug of war is already decided. So while the poetry of a universe that breathes in and out is beautiful, our universe seems to be taking one long, final exhale. Another common misunderstanding involves the scale of time itself. When we speak of the heat death or the big freeze, it doesn't mean the lights go out next Tuesday. This isn't an instant freeze, but a process so agonizingly slow it defies human intuition. The last stars will burn for trillions of years. The black holes that follow them will persist for numbers so vast we write them as 10 to the power of 100. Heat death is the definition of a slow fade, an era of deepening darkness and cold that stretches over timescales that make the current age of the universe seem like the blink of an eye. It is not an event you could witness. It is a gradual transformation into a state of permanent equilibrium, where the universe effectively runs out of usable energy over epochs we can scarcely comprehend. Then there's the terrifying specter of the Big Rip, often portrayed as the universe's violent and certain doom. It's crucial to clarify that this is not the default outcome, but one specific possibility among several. The rip hinges entirely on the exact nature of dark energy. If dark energy is a constant force, we get the long freeze. But if it is something called phantom energy, which grows stronger over time, then the rip becomes our fate. The key point is this: we do not yet know which is true. Our current measurements suggest dark energy is consistent with being constant, but the error bars in our data leave a tiny window open for the phantom scenario. The Big Rip is a real scientific prediction, but it is a conditional one, a potential timeline that depends on a property we are still measuring. It is not destiny, it is a question mark. Finally, we must tackle a fundamental confusion about the expansion itself. We often say the universe is expanding, which naturally leads to the question, what is it expanding into? The answer is both simple and mind-bending. It isn't expanding into anything. There is no empty space outside the universe for it to grow into. Instead, think of the fabric of space itself stretching. A useful, though imperfect, analogy is the surface of a balloon. As you inflate it, every point on the balloon's surface moves away from every other point. There is no center on that surface, and the balloon isn't expanding into the room around it. Its own two-dimensional fabric is simply getting larger. Our three-dimensional space is doing the same thing. Galaxies are being carried apart because the space between them is literally stretching. This means the universe doesn't need an edge or an outside. It can be finite but unbounded, like the surface of a sphere, or it could be infinite. In either case, it is all there is. There is no beyond for it to occupy. Grasping this removes a major conceptual hurdle and brings us closer to the true, strange nature of the cosmos we are trying to understand. By clearing away these myths, we sharpen our view of the genuine, awe-inspiring possibilities that lie ahead. The universe's final chapter is not just a scientific forecast, but a mirror held up to our deepest questions. If every star will fade and every structure dissolve, what does that say about our own brief lives? This cosmic context forces a confrontation with the nature of meaning itself. One philosophical response is existential nihilism, the view that in a universe without inherent purpose, nothing ultimately matters. From this perspective, our struggles, loves, and creations are just temporary flickers in an uncaring void destined for silence. The heat death renders all human ambition, all art and science cosmically insignificant. It is a stark and sobering thought, one that can feel like a cold wind blowing through the soul. Yet many thinkers and scientists have arrived at a different and perhaps more powerful conclusion. They argue that impermanence does not negate meaning, it defines it. The very fact that our time is limited, that our achievements and relationships exist against a backdrop of cosmic transience, is what makes them precious. The astrophysicist Carl Sagan often reflected on our place in the vast cosmos, noting that we are a way for the universe to know itself. In that view, our consciousness is a rare and remarkable event, a fleeting chance for stardust to contemplate its own origins and fate. The meaning is not handed down by an eternal universe, but built by us here and now through our connections and our curiosity. The philosopher Albert Camus, grappling with an indifferent universe, suggested we must imagine Sisyphus happy, finding purpose and even joy in the struggle itself, despite its ultimate futility. Your legacy may not be etched in stars that last forever, but in the lives you touch, the beauty you create, and the truth you uncover. This cosmic scale invites a profound shift in perspective. Instead of asking if our actions matter to the universe, we can ask if they matter to us, to our communities, and to the future we shape. The knowledge that the sun will one day expand and the galaxies will drift apart does not make a sunset less beautiful today. It may, in fact, make it more so. This awareness can strip away trivial concerns and clarify what is truly important, urging us to live with greater intention and compassion. The predicted end of everything challenges us to find our own fire, to create warmth and light in the time we have, not because it will last forever, but precisely because it will not. In the face of an eternal freeze, the warmth of a single moment becomes everything. The next decade will witness a revolution in how we see the cosmos. A new fleet of observatories, both in space and on remote mountaintops, is poised to collect data of unprecedented precision, data that may finally settle the debate on our ultimate fate. Leading this charge is the James Webb Space Telescope, already peering deeper into the infrared universe than ever before. Its primary mission is to witness the cosmic dawn, capturing the light of the very first stars and galaxies that ignited after the Big Bang. But for our story of the end, the beginning holds vital clues. By studying these infant galaxies, Webb is helping us measure the initial conditions of the universe with exquisite detail. This refines our understanding of how much ordinary matter, and dark energy were present at the start, tightening the constraints on our models and making our projections for the far future far more reliable. It is like getting a clearer, higher resolution snapshot of a rocket at launch, which allows us to calculate its trajectory with far greater confidence. While Webb looks back in time, two other space telescopes will stare into the heart of our contemporary mystery. The European Space Agency's Euclid mission and NASA's forthcoming Nancy Grace Roman Space Telescope have a shared monumental goal: to create the most detailed three-dimensional map of the universe ever made. They will chart the positions and shapes of billions of galaxies across cosmic history. This map is not for navigation, it is a forensic tool. By analyzing how the large-scale structure of galaxies has clumped together over billions of years, and by measuring the subtle distortions in their shapes caused by dark matter's gravitational lensing, these telescopes will trace the influence of dark energy across time. They will measure that critical equation of state parameter, the personality of dark energy, with a precision that could definitively rule out the phantom energy scenario or stunningly confirm it. These missions are designed to hunt the shadow that determines our destiny. On Earth, a new generation of giants is rising. In the high, dry deserts of Chile, the extremely large telescope is under construction. With a primary mirror spanning an astonishing 39 meters, it will gather more light than all of the existing large optical telescopes combined. Its power will allow astronomers to study the atmospheres of exoplanets in search of biosignatures, but its impact on cosmology will be equally profound. It will directly measure the acceleration of the universe's expansion by tracking stellar motions and supernova with phenomenal accuracy, providing a crucial independent check on the space telescope data. It will also peer into the hearts of distant galaxies to study the supermassive black holes there, helping us understand how these gravity engines shape cosmic evolution. Together, this suite of instruments forms an interconnected web of discovery. Each one tackles the puzzle from a different angle: the infant universe, the growth of structure, the present-day acceleration, and their combined findings will cross-verify and strengthen each other. We are unquestionably living in a golden age of cosmology. The questions we are asking are as old as humanity itself, but for the first time, we have the technological means to seek definitive answers. The data flowing in over the next 10 to 20 years will not just incrementally improve our knowledge, it has the potential to trigger a paradigm shift. We may finally close the book on the Hubble tension, understand the true nature of dark energy, and determine with high confidence whether the geometry of our universe is perfectly flat or subtly curved. This is not merely academic. These answers will point us toward the most likely finale in the cosmic story, transforming our grandest speculation into informed prediction. The forecast for the universe's end, a topic once reserved for philosophy and myth, is being written right now in the language of photons and data streams, and we are here to read it. So here we are, standing at the edge of all this knowledge with the universe's final map spread out before us. Each path leads to a profoundly different destination, from the silent freeze to the violent rip, the quantum reset to the endless cycle. Science gives us the probabilities, the data points us toward the most likely forecast, but for a moment, let's make it personal. If you had to place a bet right now, which cosmic finale feels like the one you'd put your money on? Would it be the long, cold fade of the Big Freeze, the ultimate disintegration of the Big Rip, the fiery rebirth of a Big Crunch, the instant quantum erasure of vacuum decay, or the poetic return of a cyclic rebirth? Drop your vote in the comments below, not just the name, but tell us why. Is it the one that the current evidence best supports, or is it the one that, on some deeper level, feels right to you? This is more than a game. It's a way to take this vast, impersonal timeline and make it your own. Your choice becomes a tiny part of the conversation, a human perspective etched against the backdrop of eternity. While the universe may not care about our bets, the act of placing one connects us to the story, transforming us from passive observers into participants in the greatest mystery of all. Our journey has taken us from the classic silence of the heat death to the violent drama of the Big Rip, from the quantum instability of vacuum decay to the endless poetry of cyclical rebirth. We have traced the evidence from the faint light of dying supernova that revealed dark energy's push, to the frozen ripples in the cosmic microwave background that map our flat geometry, to the gravitational shudders from colliding black holes that offer a new way to measure our expanding reality. The story of the end is no longer just a philosophical thought experiment. It is a scientific detective story written in data, and the current evidence, the best measurements from our most powerful tools, points to one conclusion as the most probable forecast. The universe appears flat, expanding at an accelerating rate driven by a dark energy that behaves, for now, remarkably like a constant force. This alignment of clues makes the big freeze, the long, cold fade into maximum entropy, the frontrunner in our cosmic finale. It is the ending our textbooks will likely teach for a generation, yet the mystery is far from solved. That critical unknown, the true, unchanging nature of dark energy, means the door remains ever so slightly ajar. Phantom energy and a big rip, a dynamic field that weakens, or even a future phase transition we cannot yet imagine, all remain possibilities on the table. The Hubble tension, that stubborn disagreement in our cosmic speedometer, is a bright flag planted at the edge of our understanding, a sign that something fundamental may still be missing from our model. This is not a failure, but the very heartbeat of science. It is the invitation to look deeper, to build better tools, to ask more profound questions. And that is where the true inspiration lies. In seeking to understand the universe's end, we are doing something extraordinary. We are a species born of stardust on a fragile planet orbiting an ordinary star, using the light from ancient galaxies and the whispers of space-time itself to piece together the ultimate fate of everything. We are the universe becoming conscious, looking back at its own birth and forward to its own potential death with awe and relentless curiosity. This quest, spanning centuries and continents, is a celebration of the human spirit. It reminds us that our meaning isn't found in defying an inevitable cosmic timeline, but in the courage to trace its contours, to wonder and to discover. So as you look up at the night sky, remember you are part of this grand, ongoing story. The final chapter is still being written, and we are here to read it. If this journey through cosmic possibilities resonated with you, consider liking this video and subscribing to join us for more explorations at the edge of understanding. And we would love to hear your thoughts. What ending feels most compelling to you, and what does this vast perspective make you feel about our place in the story? The conversation continues.